Okay, this video is totally focused on the exercise that the class did as a whole on November 28th, and I'm just going to give a video explanation for the answers rather than an actual answer key. Or the answer key is just going to be this video turned into a PDF. Okay, all right, so here's the first question. We're going to rank the following compounds in terms of their relative reactivity in nucleophilic aromatic substitution. Notice how I underlined the word nucleophilic here, italicized it, all these other issues. That's because I don't want you to rank it the same way you ranked electrophilic aromatic substitution. This is a very different reaction, okay? All right, so in nucleophilic aromatic substitution, what we're doing is we're taking an aromatic halide that has electron withdrawing groups in the ortho and para positions. This reaction is unique to this type of halide. And the net result is the replacement of the halogen by the nucleophile through a mechanism that's a lot more complex than the SN2. And that's the next question on this problem set, is to write the mechanism for this reaction using the third one. Okay, all right. So this is the reaction that we're looking at. It's very different from electrophilic aromatic substitution. We want the ring to be as electron poor as possible when we do this reaction, and we have to have strongly electron withdrawing groups, ortho or para, to our halogen. So let's look at the systems that are likely to do nucleophilic aromatic substitution. All right, so here's our halide, and here's a very good electron withdrawing group, ortho para. Excellent. Okay, halogen, electron withdrawing group, ortho para. Halogen. Yes, even fluorine works for this reaction. Actually works very well. Strong electron withdrawing group in the ortho para position. Here we have the halogen, but no, these don't work. These aren't helping because these groups are meta. Okay, so they don't help this reaction. All right, this has no EWGs, period, and this is halogen and 2 electron withdrawing groups, ortho para. Okay, all right. So we have to have the electron withdrawing groups, ortho para. The more we have, the better this reaction is. And this halogen reactivity, fluorine is our most reactive, greater than chlorine, greater than bromine, greater than iodine. And this is simply because fluorine is the most electron withdrawing of these and deactivates the ring, or makes the ring more electron poor relative to the other ones, other halogens, okay, which aren't quite as electronegative as fluorine. Okay, so this is number 1. Okay, it's got our best halogen, but more importantly, it has 2 electron withdrawing groups in the ortho and para position. This is number 2. It's got a single electron withdrawing group, and it's fluoride is the halide. This is number 3, and this is number 4. We'll say this is number 5 and number 6, but that's kind of a dubious distinction here because both of these are probably unreactive in this reaction. So probably would say that those 2 are tied for being dead last in this reaction, but there might be some activation from the inductive effect of the nitro groups in the middle one, okay, but they don't really activate the system very much. All right, so in step 2, we're going to write the mechanism, or in question 2, we're going to write the mechanism for halogen replacing fluorine. Sorry, methoxide replacing fluorine. Okay. let me get a better methoxy group. Okay, so this is our mechanism here. We're going to write this. All right. Let's not get fooled by the bond line diagrams. Let's just go ahead and draw the hydrogens so that we don't accidentally think there's no charge when there really is, or vice versa. All right, so here's our mechanism. Fluoride adds. Sorry, methoxide adds. I keep saying that. Sorry about that. All right, there's our first intermediate right there. It's a carbanion. Okay, this is why fluorine's the most reactive. It's because it makes the electron density in this ring lower than any other halogen. So fluorine helps out this very first step here. And this usually is the slow or rate determining step. Okay? All right. This halogen, or this carbanion, we can write several resonance structures, the allylic type resonance structures that we wrote for the carbocations for electrophilic aromatic substitution. Okay, we'll just draw the lone pair there too. Okay. All right, so we write the resonance structure for the intermediate carbanion. And in the second step, which is the faster step here, we just eject the fluoride like that, okay? All right. So the reason how, even though fluorine is the worst leaving group, it forms the strongest carbon-halogen bond, and it's not, the anion is more basic than any other halogen. It's not leaving in the rate determining step. So we don't see this effect in this reaction. We only see the effect of its activating the first step. All right, so let's look at this anion. I want to draw particular attention to this resonance structure right here. This is the real important one that explains why this reaction goes, where we have the anion right beside the electron withdrawing group. Okay, let's redraw that as an actual, instead of writing the words NO2, let's draw a real structure there. Okay, and we'll look at resonance structures like this in the second half of the class quite extensively when we look at carbonyl compounds. All right. We can write a resonance structure where we delocalize the negative charge onto an oxygen atom, and that's pretty good, right? Because oxygen's a lot more electronegative than carbon. All right, so there we go. And this is the really important resonance structure of them all. But what you see here is that we've stabilized the carbanion intermediate of this reaction by having nitro groups or some other strongly electron withdrawing group at the ortho and para positions. Okay, this is a synthesis problem. We're going to design a synthesis of this compound right here. And we want to make sure that we have absolutely none of that compound formed. Okay. All right. So what you can probably see here is that we're going to make the ring by an intramolecular Friedel-Crafts reaction. Okay. So a lot of people had trouble seeing this. Let me just illustrate what we're talking about here. Here's the Friedel-Crafts acylation. As a general reaction equation. Okay. Notice that the net result here is that a hydrogen on the ring gets replaced by that group there, which comes from the acid chloride. All right. So what happens if the acid chloride and the benzene ring are part of the same molecule? Okay, so I'm going to redraw this. Okay, I drew it in the all anti-conformation there, but let's draw it with an eclipsed central CC bond here. All right, so notice how in this reaction I formed that bond right there. All right, so I'm going to actually make a bond between this carbon and this carbon if I treat this system with aluminum chloride. All right, so here we go. The reaction with aluminum chloride is simply going to make a 5-membered ring. And this is where this 5-membered ring in the product comes from, right there, from this reaction right here. Okay, so intramolecular Friedel-Crafts acylation. Okay, all right, so that's our key here. All right, so that's what we want to do first, because recognize that if we do this reaction first, okay, we're going to right away make our 5-membered ring. Oops. Sorry. We'll put a bromine later, but we need a chlorine for now. Okay. All right. So there's a chlorine. All right. So we want to think about what's our reduction sequence. Okay. So let's consider hypothetically reducing it. I'll just put the Wolff-Kishner equation, but you could use the zinc HCl equation. Okay. All right, so let's, we know that we're going to have to reduce it at some point. All right, so let's contemplate whether it's better to brominate A or B. Okay? All right, so if we think about brominating A, we look at the groups. We have a chlorine, weakly electron withdrawing, C double bond O, strongly electron withdrawing, and CH2 electron donating. So this is going to be our boss, our controlling group. This is going to decide where things go. Things want to go ortho-para to this group. They can't go here. That's already substituted. They can't go there. That's already substituted. Any incoming group done by electrophilic aromatic substitution can only go right there. All right, let's analyze B. Here, these groups are equal in their ability to influence where the next, where the bromine is going to go if we treat this with Br2 FeBr3. All right, so we're not going to go here because that's between two meta groups, but these two groups are equally likely. Substitution at each of those places is equally likely. So we don't want to reduce yet. We want to brominate. Okay. There we go. That gives us there. And all we have to do now is reduce, and I'll use the Clemenson here. But recognize that we could use the Clemenson or the Wolff-Kishner interchangeably. They both do the same thing. They're mechanistically very different, but in this particular case, both of them would work equally well. Okay, all right. So this is the route we want to take. We want to go aluminum chloride first to make the cyclic compound, brominate to put bromine in exactly the right place, and do a reduction of the C double bond O using the Wolff-Kishner or Clemmensen reduction to get the final product. Okay, a lot of people did not see the intramolecular Friedel-Crafts reaction. This is an idea you're going to have to get used to in this class, that every reaction we show that's between two compounds hypothetically has an intramolecular variant where we make the two reactants part of the molecule and form a ring as a result of doing that process. There are many reactions in the second half of the class that go by a reaction like that. Okay. All right, so here's the last one. We're just going to complete reaction equations. This is just your standard sulfonation. The twist here is that it's occurring on a non-benzene aromatic compound, but remember, all aromatic compounds can hypothetically undergo electrophilic aromatic substitution. So the precursor compound we need is this compound 3-methylfuran. Okay. Substitution is more than likely going to occur here. Furan, thiophene, pyrrole. Okay, we've explained this in class. Prefer substitution next to the heteroatom. And methyl is an activator, so we want to go orthopara to methyl. This position is going to be ideal, right? Because it's ortho to the methyl and it's the adjacent to the heteroatom. This position here is meta to methyl. Okay, it's not going to be as likely. All right, here we have a fluorine that has nitros, ortho, and para to it, but the bromine also has nitros, ortho, and para to it, so both of these halogens are activated for electrophilic aromatic substitution. However, this one is more reactive. And if we very carefully add exactly 1 mole, we're going to only react at the most reactive place. All right, and so our product here should be replacement of fluorine by cyanide. Okay. All right, this next one is a roadmap problem. We're just going to supply the intermediates as we build this structure here. Okay. First one is just a halogenation of benzene. That's just going to go right there. That one should not throw anybody, okay? But now that we have something on the ring, we now have regiochemistry issues. This is an ortho-para director. Okay, all right, so remember that when we have one substituent and it's an ortho-para director, we usually get more ortho. So in this next step, we're going to just do the Friedel-Crafts acylation. At the optimal position. And this is the product that we're going to get, shown right there. Okay. All right. And notice how the group, oops, is para to the halogen. Okay. A common answer that I saw on people's papers was this one. This is really not a good answer. When you think about it, look how we have 2 carbons to the left of our carbonyl group. Here our carbonyl group is surrounded by a carbon on each side. Okay, so this is not the right structure. We add our group at the acyl carbon. There should be a bond between this carbon and this carbon. Okay, that's where we form our linkage. So that's our product. Okay, we're going to nitrate. This is a weakly electron with, this is a weak EWG. So, and this is a strong EWG. So this is going to be our boss group. And it says orthoparatochlorine. Okay. You can sort of get a clue from the final structure that this is where it has to go. It can't go para because something's already there. Okay. This last compound is nucleophilic aromatic substitution. Okay. And this is going to replace the halogen. Remember, it's got a EWG there, an EWG there. So this halogen is going to be quite reactive. And this is going to produce a compound before the Wolff-Kishner reduction. All right, and this gives us this product right here. All right, and finally, okay, and then the last step, we're going to reduce the carbonyl group to the CH2 group with the Wolff-Kishner reagent. We could have used the Clemmensen reduction. We're going to see far in the future that there's a little bit of an issue with competing nitro group reduction, but I think the Wolff-Kishner reduction doesn't do that. All right, now let's go to the last one. All right, so in this first one, we're doing an alternative Friedel-Crafts reaction. We're not using a halide plus aluminum chloride. We're using an alkene and sulfuric acid. You can see from the structure of the final product that this is where our group is going to be adding. Okay. Right, and this is what we kind of expect anyway, because naphthalines prefer substitution at the 1 position, and OH is an orthopara director. If we substituted the other position right here, that would be meta to the OH group, so this is not as good as this 1 position here. All right, so we're going to attack there. I'll go through the mechanism for this process at the end of this talk, but we're just going to substitute the group right there. All right, so this gives us this compound right here. All right, I'm just going to abbreviate this phenyl, okay, to get through this a little quicker. All right, and that gives us this compound here. We're going to treat this with sodium hydroxide and methyl iodide. You may not have seen this reaction. We're really going to discuss it in the future in the second half of the class, but it's pretty obvious that somehow or another we get an OCH3 there, and this is the step that does that. Okay, so here we are converting OH to OCH3. Okay, OME, I guess we'll put it as OME. Not going to affect this group here at all. All right, and what happens here is that we're going to treat this with NaOH to get that. Phenols have a little bit of an enhanced pKa, and then methyl iodide in an SN2 reaction is making the final product. All right. Okay, so there's the first two steps. NBS and light takes a allylic hydrogen, and that's our only allylic hydrogen right there, and replaces it with bromine. Okay. So this is our next product. Okay. And this is just the E2. This halogen, of course, is tertiary and benzylic, actually doubly benzylic, but it's more than likely with this very hindered base here going to do the E2 instead of the SN2. All right, so that's the product. Let's just look at the mechanism for the first step here. All right, so what we're doing here is we're protonating this. Let's remember where our hydrogens are. That's where we get our CH3 by this initial protonation. Okay, this is a pretty good carbocation. It's secondary, but it's benzylic. All right, this is going to react now with the naphthol derivative. That's a analog of a phenol, with a naphthalene ring instead. So we're going to start our electrophilic aromatic substitution. Let's not forget that hydrogen right there. All right, this gives us this. Okay. Here we have the hydrogen right beside the strong electron donating group. I'll just use the bisulfate anion. Okay, so it's going to remove this hydrogen like so, and that gives us product A there. Okay? All right, so that's the mechanism. And remember, as long as we can make a carbocation, we can potentially initiate a Friedel-Crafts reaction. Okay. So this is where this video is going to end. This was just the in-class problem set that I asked you to do. Okay, and so I've just made this video answer key in response to some of the mistakes that I saw, so that you won't repeat them when it really counts on the exam. Okay, all right, so this video is going to end.